Okay, we are recording. Okay, how's everybody doing tonight? How are we doing on the testing? Are we still making progress?
Yeah, I'm still locked in the 60s, so trying to break that 75 barrier.
Yeah. Well, I remember when I was going to school many years ago, I just really struggled and struggled, just couldn't quite wrap my head around it. And all of a sudden I woke up one morning and go, oh, I get it now. And from then on, it was easy. So maybe that'll happen to you. Just keep working at it. You'll get it. How's everybody else doing?
Well, I took one test, did a 65, did another one right after it, and made a 45.
Well, actually, 65, you're about right on schedule. Yeah, we're about what 3/4 of the way through. Yeah, we're at the 3/4 mark. So if you're at 65%, you're right on schedule.
I did a couple. First one was 82, the second one was 94.
Oh my goodness. Wow, you're way up there. I'd say you're
Yeah,
probably
but it took a long time. It took a long time sitting here figuring it out.
that's okay. When I took my test, it was just right before the club meeting, and it took me so long that they put me in a closet to finish the test so they could get their meeting started. So there's no time limit on it. You can take as much time as you want to.
So after you passed the test, you came out of the closet, right?
Yep, that's right. I finally came out of the closet.
Dale, I've lost the test link. If you could put that on one of your messages, I'd appreciate it.
The test link.
How to get on to take the test.
Oh, okay. What area do you live in?
Northern Idaho.
Oh, okay. So probably the Cars Club would be the easiest one. The website is called k7id.org. So if you go in there, then there's a place where you can log in to do the testing and sign up for it.
Okay, thank you.
Okay, you're welcome.
Yeah, I posted a link in the chat. That was about. I don't know. They just said you could take test online at $15.
Yeah, it is still available online. And if you go to the hamstudy.org, I think they make a list of all the places where you can do the testing. There used to be a whole lot of them. I think there's just a few left now, but there are some places you can do it online. Okay, how's everybody else doing?
Stuck in the 50s.
Stuck in the 50s, huh? Well, just keep working at it. You'll get it. It'll eventually come. What was that?
I think I have old timers.
Well, I know I have that. You're not alone there.
When you go to take the test, if you don't pass it the first time, you can take it again.
Yes, you can.
Okay.
Yeah, if you're doing the test live, if you don't pass it, they'll give you the option if you want to take it again, you can do that. Or at least they used to. I hope they still do that.
Up in Sandpoint, they do not. You take it the one time. If you're real close, within a couple of questions, they'll let you. But otherwise, you have to come back again.
Oh, okay. Yeah, each club kind of does it a little bit differently. Yeah, usually if you're close, if you only miss it by one or two, they'll encourage you to try again. And a lot of people do. A lot of people, they'll miss it the first time, and then second time around, they get it. Okay, well, let's go ahead and get started. And I know we'll get a few more people checking in here pretty soon. And anybody have any questions or things you don't understand? And let's see, let's go this one here. Go. Need an antenna for your car?
Does that car have a counterweight on the front end?
I would imagine it probably does with an antenna that size. And notice there's a rotor at the bottom. We do see some funny things with ham radio operators. They have a lot of imagination, that's for sure. Oops. You might hear the term antenna farm. Sometimes we refer to people that have a lot of antennas in their yard. We call it an antenna farm. Well, this is a real antenna farm. I believe this is in Antarctica, if I remember correctly, but I'm not 100% sure. I'm not sure exactly what they're doing with it, but that's quite an antenna farm. It's kind of an inside view of it. I think they're trying to listen to aliens or something. Okay, so tonight we're going to talk about antennas. That's kind of a very important part of the ham radio industry or ham radio business. Okay, let me start with a video here. Oops. Okay, this will kind of explain a little bit about antennas.
Okay, I'm going to demonstrate a little bit about antennas and how to check an antenna. Some of you might be familiar with that. There has to be some way to test an antenna. So let me start with that. I have my antenna is not working, so I've just got it hooked up onto a dummy load. You can get a watt meter. Most watt meters are bidirectional, so you can actually measure the power going out and the power reflected. First of all, let me explain that when the power comes from the radio, it goes up the antenna, up to the antenna, and if the antenna is working properly, it will radiate the power out into the atmosphere. But if the antenna is not working, or if it's broken or something happens, that power has to go somewhere. So it gets reflected back into the radio. And that can actually harm your radio, because if your radio is designed to put out, say, 50 watts, so it's transmitting 50 watts, and that reflected power coming back is another 50 watts. Now all of a sudden you have 100 watts in your radio, and it's not designed for that. So you can actually burn up the radio. So you don't want to be transmitting on a bad antenna for very long. So we can actually measure that if you suspect your antenna is bad, or if you just want to check your antenna. So this watt meter will actually measure the power going up to the antenna, and it can also measure the power being reflected back. Okay, so I've got this one set up here. So if we transmit forward, okay, I've got pretty much full scale there, which is about 30, almost 40 watts going forward. Now if I flip it over and look at the reflected power, the power that's coming back from the antenna, I'm measuring almost nothing, just a slight, tiny little flicker on the meter. So that's telling me the antenna is working, because the power is going out and it's not coming back. And we measure that in a ratio, the power going out versus the power coming back. We show it as a ratio, and we call it a standing wave ratio, or called SWR, because the power that's being reflected back, we refer to that as standing waves. So it's a ratio of the power forward versus the standing waves that are coming back, and we call that SWR, standing wave ratio. So if an antenna is working, the perfect antenna is a ratio of 1 to 1. What that means is 1 watt from the radio equals 1 watt being transmitted out the antenna. That's a perfect antenna. A 2 to 1 means 2 watts from the radio is only giving 1 watt out transmitted out. That means there's a watt being sent somewhere that it shouldn't be going, and it's usually coming back into the radio. So typically your SWR, you want to see it around 1.1, 1.2. If you get up around 1.5, that's you might want to check your antenna. It's not working too well. You can get these smaller watt meters. This is an old Radio Shack one, and you can actually set it up to. It has a switch on it, forward reflected, so you can measure the power forward, the power reflected. These type, you set it up forward and you adjust it till the meter, the needle is in the red zone there, indicating that's where it's set. And then you reflect it, see the reflected, it'll actually measure in a ratio, that SWR ratio. So the watt meter can tell you a whole lot about your antenna, whether it's working or not. Now I'm going to simulate a bad antenna by just loosening the coax here. Okay, so I actually took the coax off. So now I have no antenna at all. So if we look at the forward power, now if you notice the power is significantly lower than it was before. I'm only measuring about 20 watts instead of 40. And the reason for that is the radio has a built-in sensor, and it can sense the reflected power. And if it senses that there's too much reflected power, it'll turn itself down to protect the radio. So very often, if your antenna is bad, you're going to see less power than you would expect to see. And at the same time, we're seeing about the same amount of reflected power as we have going forward. So that's telling me the antenna is bad. And then if we hook it back up, now we should see nothing reflected, and we're back up to about 40 watts forward. So that's telling me the antenna is good. Now there is something about a watt meter that can fool you and make you think you got a good antenna when you don't. If you have a long coax going from your radio to your antenna, like you've got 100 foot up on a tower or something, the coax is going to have some loss in it. And depending on the type of coax you have, it can be pretty significant. So let's assume we have 50% loss on our coax. So we measure 40 watts forward, and we're losing 50% of it getting up there. So only 20 watts actually gets to the antenna. And now that 20 watts is being reflected back, which again is going to be a loss, and you're only going to see 10 watts reflected back here. So you'll see 40 watts forward and 10 watts back, which is, it's not good, but it's not terribly bad, when actually the antenna is completely broken or gone. So it can fool you. It depends on the type of coax you have and the amount of loss in it and how far away your antenna is. So just be aware of that. So that's basically how we check antennas. And I wanted to show you, actually, I wanted to bring this up. 9 times out of 10, when you have an antenna problem, it's because of water. Water gets in the connectors. Water gets in the antenna, and it will cause it to go bad or make it appear to be bad, because water will basically short out your circuit completely. Whatever power you have going up there, if there's water in there, the water just shorts it out. So you get nothing to the antenna. So getting your connectors sealed tight is very, very critical. You need to put something on there that will seal it, wrap it up with tape to make sure you've got a good, tight, water-sealed connection. And also at the antenna, make sure that it's sealed good. Now, I want to talk a little bit about types of antennas. You've probably heard the phrase high gain antenna. And you know, if you put a signal, you can put 50 watts into a high gain antenna and get effectively 100 watts out of it. And you're saying, no, wait a minute, there's no circuitry in an antenna. How can you get more power than what you're putting into it? So I'm going to simulate this balloon here. And let's suppose down inside there, this is just a small model. Our antenna is down in there, and our radiated energy is going out in all directions. Okay, this is a no gain antenna. Now, what if we took this antenna and if we flatten it like this, look what's happening to the outside edges. It's getting bigger, okay? So it's radiating more out to the sides. And so effectively, we have more power going out horizontally, but less power going vertically. So that's how we get a high gain antenna. We can actually kind of squeeze it and push more energy out where we want it to be. So what it's doing is it takes the energy that's here and just kind of squeezes it down so we shoot more power out that way. Even though we're putting 50 watts into it, effectively we're getting 100 watts out horizontally. So antennas can have gain. A 3 dB gain antenna will effectively double your power. A 6 dB gain antenna will double it and then double it again. So you effectively get 4 times the power out of it. So if you're looking for more range, the one thing you do want to be careful of though, if you're talking to a repeater, the repeater's up there, and if you squeeze all of your energy down here, you're not going to be able to hit the repeater because all the energy is going out horizontally like that. So you have to kind of balance that, decide, well, how much gain do you want? And what are you trying to do with it? Okay, an antenna can be vertically polarized or it can also be horizontally polarized. And either one works, but both ends have to be the same. So if you're vertically polarized here, whoever you're talking to has to be vertically polarized also. If one is vertical and one's horizontal, you'll get a very significant loss of energy. Let me show you that. This is a field strength meter here, and this is a vertically polarized antenna. So if my antenna is vertically polarized, you can see we got about 3/4 scale of radiated power there. Now if I turn mine horizontally, you can see that it barely even moves the needle. So it's actually a ratio of about 100 to 1. By having the antenna vertically polarized, and if you're vertical at the other end, you get 100% efficiency. But if you turn one end horizontal and the other end is vertical, you're going to reduce it by about 100 to 1. So it just has to be the same. Most of the UHF and VHF in the area uses vertical. The only time we really use the horizontal is when you get down in the HF bands, the low, what I call low band. A lot of times they're horizontal, and I'll talk about that when we get back into the classroom about the advantages of that. So most everything is vertical. So if you're using a portable, you need to make sure that the antenna is straight up and down. You see in the movies where cops talk in radios like this, that doesn't work. You're going to reduce your signal so much that nobody's going to be able to hear you. So when you're talking, you need to talk with the antenna vertical and talk right into the microphone. Oftentimes we get people that hold radios out here and talk. That doesn't work too well either. So it's very important that the antenna is straight up and down in order to get your signal to where you're trying to talk to. Okay, let me talk just a minute about feed lines, or coax as it's called. Do you know what the term coax means? It's actually a mathematical term. Coax means equal distance from a center point in all directions. In other words, it's perfectly round. Let me show you like this one here. See, it's perfectly round with a center conductor in the middle. And it's very critical that the coax maintains that round shape. If you If you damage it, like this one here, see how this is flattened like that? Okay, that's a damaged coax, and you're going to lose power, but because of that. Your coax needs to be round. You need to keep it perfectly round. So don't walk on it, don't step on it, don't put things on it. You want to keep it up off the ground so that it doesn't get damaged. There's a lot of different kinds of coax out there. There's advantages and disadvantages to some. Probably one of the most popular is called RG58, and it's just very small. We typically use these in vehicles for mounting mobile radios, and they work really good because they're very flexible. They're easy to run through headliners and stuff, but these have a lot of loss in them. You probably don't want to run more than about 20 feet of this. Otherwise, the loss is going to be so much that it's not going to be worth it. I've seen some people run 100 feet of this up a tower, and it just doesn't work. You don't have any signal left by the time you get to the antenna. So these are mostly for in vehicles. That's what it's designed for. It's called RG58. Another grade of coax, this is a step up. It's called LMR 400, or there's a 9913. There's several different models of it. And it's about almost a ½ inch in diameter, a lot stiffer. It doesn't bend quite as well. But the loss is a lot less on this. So if you're running a long run, you probably want something of this nature. Even RG8 is okay. It's kind of a low end, but you want the bigger coax so you don't have as much loss. Now, if you really want to get up into the big stuff, you can get up into this. This is called Heliax. Or sometimes referred to as hardline. It's very stiff. It doesn't bend very easily at all. But if you're running a long run of coax, the loss on this will be significantly less than some of the other types of coax. So, but it's a little spendy too. It's about $1.50 a foot. So unless you're really serious about it, and then you can get up into this is called Superflex, and it's a more flexible version of that. It just bends easier, but it still has very good properties. It's very low loss. And then if you want to get really serious, you get up into this stuff here. This is 3/4 inch, I think it is. 3/4 inch hardline or Heliax. And it's about $2 or $3 a foot, $2.50 to $3 a foot. There again, but super, super low loss. And to answer your question, yes, it does handle more power, but that's not really the reason for it. The primary reason is because of the low loss. And then if you get up into cellular type coax, this is what they use on cell phone towers. It's 1.5 inches in diameter, and it does not bend very well at all. I mean, I don't have enough strength to bend it here. But it's super, super low loss. You can run 150, 200 feet at 900 megahertz and get very little loss on it. But it's expensive. It's about $15 a foot. So unless you really want to get into it, that might be a little spendy. This is called RG8, which is very similar to the LMR 400 or the 9913. RG8 is good, but the braid on it is not as tight. So it does have a little more loss than the LMR 400, but it's still very good coax. If you're going to run a long run, you probably want to do something like that. We do have some of these type flavors of coax. This is actually a double shielded. It's kind of expensive, but it's silver plated. The metal in there is actually silver plated, and it's double shielded. So it's super, super good coax, but it's pretty spendy. Probably around $1, $1.50 a foot. And then there's some other flavors. This type of coax is really good, but it's very lossy. Has a lot of loss in it, so it's only good for very short jumpers. You don't want to use more than 4 or 5 feet of it in any one spot. And there's a lot of different types of connectors that are available. You probably can't see these connectors. This type here, it's called a PL259, very popular. That's usually what screws into the back of your radio. And this type connector has been around forever and ever. Back in the early days when they first started producing coax and connectors and things like that, they took all the connectors and lined them all up, and they just numbered them. 1, 2, 3, 4, 5, 6, and so forth. This happens to be PL, means plug number 259. So is number 259 in that huge lineup. Now, when the military came along, they had their own flavor, and they said, no, we don't do things the way civilians do. We have to do it different. So they took all of their connectors and lined them all up, and they called them type A, type B, type C, and D, and so forth. Well, this one is type N in that lineup. It's called an N connector, and it's still used today. The N connectors are much, much better than the PL259s. The PL259 has a lot of loss. It's oftentimes referred to as a UHF connector because it's good only up to about UHF frequencies. If you get any higher than that, this has got too much loss in it. Whereas this will go clear up into the gigahertz range, has much less loss in it. But most of your radios on the back of the radio, that's what you're going to find is the PL259. And there's a whole bunch of other type connectors. This one's called a BNC. You'll find those on scanners and places where you're not really transmitting any power. And they're okay, but they're not good for transmitters and things like that. And there's a bunch of others. This one's called a TNC. This was actually invented by GE back in the days when Motorola and GE were fierce competitors. And GE came up with this connector and said, this is the future of two-way radio. Everybody's going to go to this connector. Well, it didn't happen. There's a few things that use it, but not much. They're not very popular. And then Motorola came up with their flavor. They call it a mini UHF. It looks just like the UHF connector, but it's a mini version. And Motorola said, oh, this is the future of two-way radio. Everybody's going to go to the mini UHF. Well, Motorola is the only one that uses it. So there are a lot of different connectors out there, and it's just a matter of how much loss they have. The type N is probably the best of the bunch. TNCs are okay, not too much loss in them. The mini UHF I haven't been terribly impressed with. They don't seem to perform as well. But probably for ham radio type stuff, the UHF connector is about all you're going to see. This is another type of coax. This is called 1/4-inch Superflex. It's a really good coax, but it has a lot of loss. There again, it's only for short runs, and it's somewhat flexible. Not as flexible as some of the other cables, but these are sometimes used at repeater sites and commercial type applications. So that's just kind of a rundown on the connectors and the cables. This is, you may have remembered this from back in the days of television with the old antennas up on the roof. It's called twin lead. Sometimes ham radio people call it ladder lead because some of them have little holes in it, makes it look like a ladder. And it's used in HF band frequencies sometimes, not very often. If you get it just right, it does work really good, but it's extremely careful. You have to be away from everything. You have to have standoffs to get it out away from buildings and away from other objects and so forth. But once in a rare while, you'll still see this used in ham radio. There's a lot of different flavors of that. Okay, so that's kind of a rundown on antennas and coax and cables and how to check a watt meter or how to check an antenna. So let's go ahead and go back to the classroom and we'll talk about some of that stuff a little bit more.
Okay. Now let's go back to. Okay, so that's kind of an introduction to antennas and coax, or sometimes we call it feed line. So this is kind of a diagram. Now you can't see energy that's radiated out into the atmosphere. So, but this is a kind of diagram. If you could see it, it might look something like this, where your antenna is down in the center, down in here, and the energy is pretty much radiated in all directions, including going up and down. The antennas do work good, and you can typically transmit from your antenna here out this distance right here. That's about the range on it. But if we go to what's called a high gain antenna, basically what we're going to do, oh, my button quit working. So basically what we're going to do is we're going to compress it down from the top and the bottom, which is going to cause it to spread farther out on the sides. So, so now instead of being able to talk from here to here, we can now talk from here all the way out to here. We can gain more distance by having a higher gain antenna. So the higher gain antennas are quite popular because it gives you more coverage. You can transmit farther. And antennas can be rated. They're typically measured in the amount of dB gain. This is a side view. This would be your antenna right here. So if we go to a high gain antenna, you can see it pushes more energy out this direction and not so much up and down. So it keeps it more flat, so that way you can talk a greater distance. And from the top view, there's no difference. It's still omnidirectional. It radiates in all directions. Okay, there's another term. It's called a Yagi antenna. And there are some test questions about these antennas like this. A Yagi is a directional antenna where it transmits most of the energy in one direction and very little in the other direction. So in a case of a Yagi antenna, this is our antenna right here, and you can see we're pushing a lot of energy out this direction here. So it'll transmit very far away, and there's very little coming off the back side. It only goes a short distance. We sometimes call this the back lobe or the rear lobe of the antenna. It does transmit some, but not nearly as far. And from the top view, it not only squeezes the energy down, but it also squeezes it in from the sides. So from our antenna right here, you can see we're getting a lot of energy in this direction, and there are some side lobes there, so you do get some energy over here, but not very much on the back side. So it's designed to concentrate the energy in one direction. So you can talk a long ways on a Yagi antenna in one direction, but not in all directions. Okay, there's a term called dB. It means decibel. And the gain or loss of an antenna is measured in decibels. There is an actual mathematical formula where you can calculate, if you're putting out 50 watts, you can calculate how much that is in decibels. But we're not going to get into that because there's nothing on the test about that. But just as an example, as I mentioned in the video, a 3 dB gain is basically double. So if you have 50 watts out your radio, you can actually, by getting 3 dB gain, you can radiate 100 watts. And 6 dB is where you double it and then you double it again. So it's actually going to be 4 times as much energy with a 6 dB gain antenna. And then a 9 dB, you're going to double it, and you're going to double it again, and then double it again. So then you get a lot of energy way out here and almost nothing going up or down. For the most part, we're not talking to airplanes, we're not talking to submarines. So if we keep the energy more on the horizon, we can actually get more range out of it. And this is another graph of the same thing. This is a 0 dB or a no gain antenna, and a 3 dB and a 6 dB. Now, physically speaking, I have here, these two antennas right here are both VHF antennas. This one here is referred to as a unity gain antenna. It has a gain of 1, which is no gain at all. And this is basically a half a wave. Well, the antenna itself is actually a half wavelength long. So if we're in the VHF band, which is the 2-meter band, so half a wave would be half of a wave would be 1 meter. So 1 meter is roughly about 18 inches or so. Okay, so this would be a unity gain antenna. And they do work well, but a high gain antenna works even better. So again, still in the VHF band, this would be a high gain antenna, which is, let's see, oh, this one's a quarter wave, and this one's a half wavelength long. Oh, I told you wrong on that one. This one over here is actually a quarter wave, which is roughly about 18 inches. Okay, so this one is going to be a half a wavelength long, which is 1 meter. So 1 meter is roughly about 3 feet or close to 3 feet. So the antenna is much taller, but it radiates more horizontally, so you get more gain out of it. And typically speaking, the bigger the antenna gets, usually it's more gain on the antenna. And as the antenna gets smaller, it's less in gain. Now, if we get up into the UHF band, this is up in the 440 megahertz band. Here's 3 different sizes. Okay, this is a unity gain. It has a gain of 1, and it's a quarter of a wavelength long. So in the UHF band, a quarter wavelength is 70 centimeters, which is 7/10 of a meter. So if you calculate that down to a quarter of a wavelength, so we're going to subtract 3 dB and then probably subtract 3 dB again, and it's going to come out roughly at about 4 inches tall. So it's not going to be very tall antenna, just a little short, 4 inches or so, and that will produce a unity gain signal. So it radiates in all directions, and it radiates up and it radiates down. Then if we go to this one here, this is a half wave, which is a 3 dB gain. And so a half wave at 70 centimeters is 35 centimeters. Okay, which roughly comes out to be about 2 feet long, I think it is. I'd have to calculate it out. But that would be a half wave antenna. And usually half waves I don't see many of those. Now this one is actually an interesting antenna. It's a 5 dB gain antenna. And the way they're doing it is this right here is a half wave UHF antenna from this coil right here to the tip. That's a half a wave antenna. And then down here, this is a quarter wave, an antenna. So it's going to be roughly about 4 to 5 inches down here, and it's going to be roughly about 2 feet or so up here. And this coil actually makes it so that you can stack one antenna on top of the other. And that's how they're getting high gain out of it. But that's typically about a 5 dB gain antenna. So that's why there's so many different kinds of antennas and so many different sizes, because it determines how much gain there is on whatever particular band that you're working in. Okay, now let's talk a little bit about coaxial cable. We sometimes call it feed line. And this is what carries the energy from the radio up to the antenna. And the whole idea is we want to keep the energy contained within the coax so we don't get any leakage, because we want to get all the energy we can up to the antenna. So typically coax has a shield on the outside. This one is actually double shielded. This is tinfoil right here, a tinfoil shielding, and then there's galvanized steel braid on the outside. So that keeps it well shielded, which keeps the energy inside the coax. And then this is the center conductor. That's where the energy actually travels. Okay, here's a little bit closer picture up. I know you probably couldn't see in the video very well. This is that Heliax I was telling you about, this hard line. And incidentally, the prices are a lot more now than they were when I made this video. This is probably closer to $3 or $4 a foot now. But this is that Heliax. And like I mentioned in the video, it can carry more power, but that's really not the purpose of it. The purpose is to make it with less loss. All coax has loss, but it's how much we want to try to keep it minimal, as less loss as possible. So that's what this big, heavy, hardline coax does. Is just it transmits the signal from the radio to the antenna with as minimal loss as possible. Okay, this is another coax. It's called RG8. It's very popular in ham radio, especially down in the HF bands, what I call the low band frequencies. It's quite popular. The only thing that makes this one a little bit of a disadvantage is this braid right here. It's only a single shield on it. There's no second shield. And this braid is actually woven very loosely so that some energy can actually radiate out through the coax itself. So it's probably not as popular, but there are some people that still use it. This one is very popular coax. It's called LMR 400. And this has double shield. You can see there's tinfoil right here, and then there's braid on the outside of that. So it's a double shielded, and this is the center conductor. And LMR 400 is good coax, pretty low loss, and it's good if you have a tower. You know, if you're running to like 50 feet or more to get from the radio to the antenna, I would recommend going with like an LMR 400 or something equivalent. 9913 is also an equivalent of the LMR 400. So whatever they call it, that's good coax. And then this is that small coax I was telling you about. It's called RG58, and it's really easy to work with. I mean, it's very, very flexible. You can run it through the headliner of your car. You can run it under the carpet of your vehicle. It's very easy to work with, but the problem is this has a lot of loss. The loss is actually very heavy with this type connector. Okay, so, oh, bless you. Okay, these were some of the connectors that I was showing in there. I know you couldn't see them in the video very well. We call this a UHF connector. It's actually a PL259. You'll also hear the term SO259, which is just another name for the PL259. But this one is very, very common, and usually most cables where you plug it into the back of your radio, this is the connector you're going to use. Okay, this is called a BNC. It's a bayonet style connector, and it's been around for quite a while. Typically these you don't see on transmitters because it's not that type of a fitting connector. But you see these on scanners, and you'll see them on sometimes Wi-Fi type connectors. They're things where you're not transmitting a lot of power into them. Okay, now this is that, remember I was telling you in the video that, you know, the civilians lined up all their connectors and they just numbered them. There's 101, 102, 103, and so forth. And this one, this one here is actually PL259. So it was, the connectors were up to 259, and that's the one that got the name there. But the military does theirs differently. This is called a type N connector. It's just, and again, that military had that big long lineup. They had, you know, type A, or type B, type C, and so forth, all the way down. When we get to the letter N, that's where this connector lives. So these are really good. They're very efficient. They are more expensive, but they are They're just very good connectors, and they're good ones to have around. Okay, this one is called a TNC, and this was invented by GE way back in the day. And GE announced that this is going to be the future of all two-way radios. Well, it didn't go very far. GE used it, and that was about it. Okay, this one is called an SMA. It's a very small connector, and this is a lot of times you'll see antennas. They're screwed onto portable radios using an SMA connector. Or sometimes special applications, even Wi-Fi can sometimes use an SMAs. So I'm not going to talk about it here. Let's see, not too much. Sorry, I lost my train of thought. Okay, so this is yeah, the SMA, you'll see that's usually what's on the portables, your portable radios. When you screw your antenna in, that's an SMA connector. This one is a type F, and again, it's that military designation. And this is typically what you see on television coax. This is what screws into the back of your television or screws into your splitter and so forth. And television coax is a little different, but that's called a type F. So those are just a few. There's actually a lot more than that out there, but I doubt you're ever going to see much more than about these. Okay, antenna testing. We talked about that in the video. You have your radio, and there's a piece of coax that goes up to the antenna. And the testing can actually be done at the radio. You don't have to climb the tower. You don't have to get up on the roof or, check the antenna. You can test it right at the radio itself. So we're going to measure, this is what's called forward power. That's the power that comes out of the radio and feeds up into the antenna. Okay, now if the antenna is working good, there will be no reflected power, which is rare. I mean, electronics and radio is just like anything else. There's no such thing as perfect. So there's always going to be, or almost always going to be, a little bit of reflected power. And we refer to that reflected power as standing waves. So that comes back down from the antenna back into the radio. Okay, now we want the reflected power as low as possible. You want as little possible power getting reflected back into your radios as you can. But sometimes there is some. But we measure this in a ratio. It's a ratio of the amount of power going out versus the amount of power that's actually being reflected or radiated out into the atmosphere. And like I mentioned in the video, a perfect antenna is a ratio of 1:1. That means 1 watt from the radio will get you 1 watt of energy radiated out into the atmosphere. A 2:1 means you have to have 2 watts of power from the radio to get 1 watt transmitted out into the atmosphere. So you're losing about 50%. 3:1 is going to be down, you're going to lose 2/3 of your power. So like I mentioned, all coax has loss and all connectors have loss. So it's just a matter of how much loss, how much can you afford to lose. So you want to plan your coax and your connectors. You want to use as few connectors as possible because each connector does inject a little bit of reflected power. So keep it at a very minimum. Normally you just want a connector at each end and that's it. Too many splices in the middle can really affect your signal a lot. Okay, so those are called standing waves, and this is a standing wave ratio. That's what SWR stands for. And I think there are some test questions about this, but this SWR is just a way of measuring the standing waves. Okay, so we want that as close to 1:1 as you can get. Okay, many watt meters have they're directional. You can measure forward power or reflected power. This particular one can measure both of them at the same time. It actually has 2 needles in there. as you can see, this needle right over here, this measures the forward power. So it follows the scale up here. And then this one is measuring reflected power, and it follows the scale up here. So a good antenna is you want maximum forward power and minimum reflected power. And sadly to say, we just found out that MFJ is closing their doors. They're going out of business. They've been a big name in ham radio for a long time. Antennas and watt meters and stuff like that. So we're going to miss them. Okay, let's talk a little bit about RF propagation. Propagation is the ability to radiate energy out into the atmosphere. And unfortunately, we don't live in a perfect world. There's a lot of obstacles out there. There's mountains, there's buildings, there's things that get in the way that will cause your signal to not get where we want it to be. But there are some things that do help. This is one that's called knife edge refraction, where typically if you're transmitting a signal, say you've got a transmitted signal here, the energy goes up to here, and as it scrapes across the top of the peak, it will splinter, and you get different waves of energy going in different directions. And sometimes one of these will actually come down and be able to talk to somebody on the other side. And sometimes when you're transmitting on a radio, you think, wow, that's cool. I got over the mountain. How'd I do that? Well, this knife edge refraction can do that. So that's there are some test questions about that, or they call it knife edge propagation. So that's when you can actually get a signal over or around an object where you don't have direct line of sight. Okay, picket fencing. This is something that happens a lot, and a lot of people don't understand it. Oftentimes you get people trying to check into a net, or they're trying to talk on the radio, and their radio is just really scratchy and noisy. You can hardly understand them. And you ask them to move just a couple of feet. So they step over a little bit, and all of a sudden they're crystal clear. And they're going, wow, how did that happen? Okay, the way that happens is because the signal, especially when you're in like a city environment where there's buildings and obstacles and stuff, the signals bounce around a lot, bounces off of all kinds of things. And here you can see the signal is just bouncing off all of the different buildings. Okay, so I'm going to kind of demonstrate to you how this how this picket fencing works, or how it does what it does. Okay, we have two radios here, one at the top and one at the bottom. So the bottom radio is going to radiate a signal, and it's going to transmit out like this. And some of the signal will actually reach the other radio. Now that's if there's no obstructions, there's nothing in the way, you're on flat ground, and you're able to talk from here to there, which makes it nice. But a lot of times that's not the case. So let's put a building in the way. Here's a big building. It's now blocking the signal and making it so that the other radio is not receiving anything. So what happens is sometimes you get, let's say there's another obstacle, like another building or something, and this energy is going to the second building, and it's reflecting off of the building. And we can get a signal that reflects this direction. So now you can actually hear it even though you're behind a building, because it's bouncing off of something. But now let's suppose there's another building over here, or another obstacle, and it is also reflecting. So it can reflect a signal like this. So now you have two signals that are crossing paths. And if you're moving, if you're traveling, sometimes, if you're moving through here where the lines cross like this, the signals will actually add together. You'll double the signal strength. Then when you go in between, the two signals cancel each other out. And then when you come back to here, you get a good signal. Or if you're up here, you get a really strong signal again. So as you move across here, it goes from nothing to strong signal, to another strong signal, to nothing, to strong signal. And it can cause it to fade in and out. And the faster you go, the more it sounds like just a flickering sound where you're just very rapidly chopping in and out. And this is because of that picket fencing effect. And it happens a lot. People don't realize it, but especially when you're talking on a portable, a small radio, it's very noticeable. Where if you're, sometimes you hear somebody driving and they're talking on the radio and you can just hear it chopping in and out as they're going. Well, that's because of that picket fence. It's because we don't have a line of sight path from here to there. It's being reflected off of something here and it's being reflected off of something here. So we're getting these two signals that cross each other, and it will either add together or it will subtract from each other. They'll cancel each other out. So that's a very common thing. It happens a lot. Oh, one more signal. Okay, building penetration. A lot of people ask me, well, what's better, UHF or VHF? And my answer is yes and yes. It depends on what you're doing. If you're typically in like a city environment where there's a lot of buildings and houses and a lot of structures, the UHF tends to penetrate buildings better than VHF does. And the reason for that is when the signal is trying to penetrate through a building, it has to find an opening somewhere. It's either a window or a door or a vent or a hole in the wall or something where the signal can get through. And the hole has to be at least a half a wavelength in diameter for the signal to get through. Well, a half a wave diameter for the VHF signal is about 2 feet. Okay, so you have to have a hole that's at least 2 feet in diameter for the signal to get through. But in the UHF band, it has to have a signal that's a half a wavelength, and that's only going to be about 10 inches. So it can get through a much smaller hole, a much smaller opening, and there's a lot more small openings than there are big openings. So generally speaking, UHF does seem to penetrate buildings better than VHF does. But on the other hand, if you're out in the outdoors, up in the mountains and the hills and so forth, the VHF will tend to bend a little better. So if you're on, talking over a hill or a mountain, the VHF will tend to bend and follow the curvature of the land, whereas the UHF is more line of sight. So it doesn't bend over hills and stuff. So it just depends on where you are and what you're doing. One can work better than the other. But it's mostly because of the environment. Okay, antenna polarization. We talked about this in the video. Most of the UHF and VHF radios use vertically polarized antennas. And so typically if you're talking on a portable radio, you want your antenna straight up or straight down. You can do it straight down too, as long as it's vertical. But down in the HF band, or what I call the low band, they typically use horizontal antennas more. And the reason for that is the horizontal antennas, or the HF band, when it's horizontally polarized, will tend to follow the curvature of the earth a little bit better. So if you're trying to transmit beyond the horizon, the horizontally polarized signal will tend to follow the curvature a little better than the vertically polarized. So most of the HF stuff, they use horizontally polarized antennas. And either one will work, but both ends need to be the same. Whoever you're talking to needs to be polarized the same direction you are. Okay, this is a term you may have heard before, skip signals, where you can bounce signals off the atmosphere. And looks like we're running out of time, so I'm going to have to kind of hurry a little bit. The ionosphere, the atmosphere there's multiple layers of atmosphere, and there's one called the ionosphere. And it's quite a ways up. It's pretty high altitude, but the ionosphere is where you can bounce most of your signals. So if you have a transmitter over here, you can actually transmit, bounce it off the ionosphere and talk to somebody pretty near halfway around the world. We call that a skip. where you're skipping the signal across the atmosphere like that. And the HF bands, that is very common. We can do that a lot. UHF and VHF, not so much, because the higher frequencies tend to just penetrate through the atmosphere and just keep on going. They don't bounce, or they don't reflect very well at all. Sometimes you can have multiple bounces where you can transmit and off the atmosphere, bounce it off the earth, back up to the atmosphere, and bounce it 2 or 3 times to get, halfway around the world. Sometimes that can happen also. And again, the angle of your antenna can have a lot to do with it. If your antenna is pointed mostly vertically, where it's kind of almost straight up, the signal is going to bounce and come right back down, and it's not going to be very far away. But as you have the antenna pointed more towards the horizon, you can bounce here and have it come down clear over here. So typically the HF antennas are usually pointed pretty much right at the horizon, because you want to bounce off the atmosphere as far away as you can so that you can talk someplace, around the world. Okay, there's another term called tropospheric ducting. Say that 3 times fast. And this can happen occasionally. And it can actually happen with even UHF, VHF, HF bands. Any of them can do it, where you have what's called a temperature inversion, where you have cool, dry air above, and there's cool, dry air below, but in between, there's a layer of warm air. And that kind of acts like a duct. Have you ever played around like in a building or something where they have heater ducts all over the building, and you can put your face right up to one of the grills and talk, and somebody in another room can hear you? Because your voice will follow the ductwork, the heating and cooling ductwork, and come out in another room. Well, it kind of does the same thing in the atmosphere, where you can actually get a signal trapped up in that warm layer and have it come out somewhere else. But those are very dependent upon weather. It's not something, in fact, you can probably not even predict it. It happens when it happens. Okay, there's another term called meteor scatter, where you can actually bounce a signal off of a meteor tail. And a lot of the ham radio people get really excited anytime there's a meteor in the area, because they want to bounce the signal off the tail. And you can do that. It does work. You have to, have the conditions just right and the antenna pointed just right and so forth, but it's a doable thing. There's another term called tropospheric scatter, and that's where you're basically bouncing a signal off of the pollution that's in the air, the dust particles, the pollutants, whatever's in the atmosphere. You can sometimes
Chemtrails.
The what?
Chemtrails.
Chemtrails?
Yeah, bouncing off of chemtrails.
Oh, okay. Yeah. So that is something that can happen. And you can bounce a signal off of there and come out somewhere else in the world. So that's another method. And there again, it's very difficult to even predict. And sometimes when you're transmitting an HF, you're not sure how it's getting there. It's just one of these methods. It's difficult to tell, but these are different ways that it can bounce and skip, and you can get talk to somebody, I mean, literally all the way around the world. Northern Lights, you can actually bounce signals off it's called the Aurora Borealis. You can actually bounce a signal off of those lights. The only problem is the lights don't stand still. They're constantly waving, they're constantly moving, and so your signal's going to be constantly shifting in and out. But you can do it. It's just a fun thing to play with. Okay, we're just about out of time, so I just wanted to kind of go through the test questions real quick. I'll let you read them on your own. But these are questions concerning antennas and transmission in the atmosphere. So what should you do if another operator reports that your station's 2-meter signals were strong just a moment ago, but now they're weak or distorted. Okay, there again, this is that picket fencing effect. Try moving a few feet or changing the direction of your antenna, because that picket fencing, just a couple of feet can make a huge difference.
So, Dale,
Yes.
is that similar to like on a cell phone? Sometimes, you're talking to somebody and it's really a bad signal and they move a little bit and then it's better.
Yep, it can do that. Yep, cell phones can do the same thing, because really a cell phone is just a two-way radio. So they just operate in a higher frequency band. But yeah, they can do that. Although cell phone, a lot of times you can just move a few inches and make a huge difference.
It's the same principle.
Yes, it is. It's the same principle. Yeah. I've had a lot of times where I got a really bad connection. I just move a little bit and it clears right up. So that, yeah, that can happen. What might the range of a VHF and UHF signal be greater in the winter time? Well, because the leaves and foliage on trees during the wintertime, all that falls to the ground, because the leaves do tend to absorb some of the signal and some of the green and the foliage and so forth. So a lot of times in wintertime, you'll get a better signal than you will in the summertime. What antenna polarization is normally used for long distance, weak signals, CW, single sideband, and so forth, using the VHF and UHF bands? That's generally horizontally polarized. Most of the HF stuff is, anytime you're trying to talk long distance, it's normally horizontally polarized. Doesn't have to be, but generally it is. What can happen if the antenna is opposite ends of a VHF or UHF line of sight radio link are not using the same polarization? It's like I showed you in the video, when one's horizontal and one's vertical, you're going to lose a significant amount of signal. So your signal will be much weaker. When using a directional antenna, remember this is that Yagi antenna I talked about? How might your station be able to access a distant repeater if buildings or obstructions are blocking the direct line of sight path? Well, sometimes you can aim it and bounce off of something else and get a signal path. Bounce off of another building, off a mountain or something, and you just have to kind of try it and see. Just move the antenna a little bit. Sometimes if you're using a directional antenna, you're not pointed where you're trying to talk. You might be pointed off to the side. So that's, yeah, try to find a path that reflects the signals to the repeater. And there's no way of really predicting it, just to try it and see till you find something that works. What term is commonly used to describe the rapid fluttering sound sometimes heard from mobile stations that are moving while transmitting? And again, that's that picket fencing effect, where if you're driving or moving, you can get that rapid fluttering sound. That's because your signal is very rapidly fading in and out. What type of wave carries radio signals between transmitting and receiving stations? It's called electromagnetic. All of the radiated energy is electromagnetic. Which of the following is likely cause of irregular fading of signals received by ionospheric reflection? And again, it's that picket fencing type of effect where you get a random combining of signals, and the signals are coming from different directions, where sometimes they'll combine and add together, sometimes they'll cancel each other out. And once again, you just move a few feet and sometimes can make a huge difference. Which of the following results from the fact that skip signals refracted from the ionosphere are elliptically polarized? Okay, elliptically polarized means that it's both horizontal and vertical, which sometimes can happen. Sometimes when you're transmitting a long distance, using the HF band, the signal can actually twist, so that you might be transmitting it horizontally and it can twist and come out vertically, or even a combination of both vertical and horizontal. So in that case, either vertically or horizontally polarized antennas might be used. fact, you'll notice on if you've seen anybody that has a tower with a big HF antenna, sometimes they have two rotors on there. You can point the antenna in a certain direction, and you can also tilt the antenna to either vertical or horizontally polarized. Because sometimes great long distances, it will shift, or it starts out horizontal and ends up vertical. Okay, what may occur if data signals arrive via multiple paths? And again, it's that picket fencing effect. In this case, you're going to get a lot of error rates because of the fading of the signals fading in and out. Which part of the atmosphere enables the propagation of radio signals around the world? And that's that ionosphere. That's the layer. In the atmosphere, there's multiple layers up there and they all have different names, but the ionosphere is the one that bounces signals. How might fog and light rain affect radio range on the 10-meter and 6-meter bands? Okay, on the low band frequencies, fog and rain doesn't really affect it very much. But as you get higher and higher in frequency, it can affect it quite a bit. If you get up into the microwave, sometimes fog and rain will completely wipe the signal out. But down in the low HF bands, the low band frequencies, it has very little effect. Okay, what weather condition would decrease range at microwave frequencies? And there again is, precipitation, rain, fog, and that type of thing. It can definitely slow down microwave. In fact, I've seen microwave links go completely off the air because a rainstorm or clouds and stuff move in, can completely stop it. And once the rainstorm passes, the microwave comes back on. What property of a radio wave is used to describe its polarization? It's actually the orientation of the antenna is what determines the polarization. Or in this case, they're saying the orientation of the electric field. So the antenna would be the electric field. The radiated energy is the electromagnetic field. What are the two components of a radio wave? That's electric and magnetic. Electric occurs within your equipment. It's within the radio and the antenna. The magnetic is what occurs out into the atmosphere. So we usually say it's electric and magnetic, or it's called electromagnetic. What are direct, or not by a repeater, UHF signals rarely heard from stations outside your local coverage area? Let's see. Oh, the UHF signals are usually not reflected by the ionosphere. As you get higher in frequency, the atmosphere has less and less effect on your signal. Once you get up into the UHF band, pretty much none of it gets reflected because it just penetrates through the atmosphere and just keeps on going out into space. So only the low band frequencies are the ones that are reflected by the ionosphere. Which of the following is an advantage of HF versus VHF and higher frequencies? Okay, so the long distance ionospheric propagation is far more common in the UHF band. In fact, it's actually quite rare in the VHF and UHF bands. If any of you have ever played with CB radios years ago, it used to get a lot of skip. Sometimes you can hear people talking clear on the other side of the country. Well, CB is in the HF band. So that will definitely reflect off of the atmosphere. Okay, what is a characteristic of VHF signals received via auroral reflection? That's the northern lights. The signals exhibit a rapid fluctuations of strength and often sound distorted. And it's because the lights are constantly moving. They're shifting all the time. And so your signals will be constantly fading in and out, moving. And it's actually pretty difficult to talk over reflecting off the northern lights. But you can do it. And some people do it just because they can. Which of the following propagation types is most commonly associated with occasional strong over-the-horizon signals in the 10, 6, and 2 meter bands. Okay, that can be that sporadic E. That's where we were talking about the reflecting off the stuff that's in the atmosphere. But that one's kind of sporadic. It depends, if the wind blows, it shifts around. But it can be used. And where you get occasional strong over the horizon signals, but not always. It's kind of unpredictable. Which of the following effects might cause radio signals to be heard despite obstructions between the transmitting and receiving stations? And this is that knife edge diffraction that we talked about, where the signal, as it breaks over the top of a mountain or over the top of a building, can often splinter, and you get little radiating patterns on the other side. So sometimes you can actually talk to somebody on the other side of the mountain, even when you would look at it and say, nope, can't do that. But sometimes it can happen. What mode is responsible for allowing over-the-horizon VHF and UHF communications to ranges of approximately 300 miles on a regular basis? This is that tropospheric scatter we talked about. That's basically the stuff in the atmosphere. And sometimes those can happen in the UHF and VHF bands, but they're not really common. Like it says here, about 300 miles or so. But it does happen occasionally. What band is best suited for communicating via meteor scatter? That one tends to work best in the 6 meter band. I'm not really sure why, probably because of the length of the tail and the material it's made of or something. What causes tropospheric ducting? Remember, that's when we talked about the different layers of atmosphere where you get it's a temperature inversion, where you get cold air on the top and cold air on the bottom, but there's a warm layer in between. So that would be, D, temperature inversions in the atmosphere. What is generally the best time for long distance 10 meter band propagation via the F layer? The F layer is one of those layers up in the atmosphere. Okay, so the best time is from dawn to shortly after sunset. In other words, basically daytime. Oh, I forgot to mention that this ionosphere does change between, especially between day and night. It's affected a lot by the sun. When the sun is shining, when it's a bright day, the ionosphere is actually higher and allows you to reflect better. But at nighttime, it comes down really low and it doesn't reflect as well. So yeah, for the long distance 10 meter, so it's basically from dawn, which is daylight, to shortly after sunset. But during the nighttime, not so much. And also sunspots will affect it too. Sometimes when there's a storm on the sun, that can cause it to either work or not work better. Usually I think it causes it to not work. Which of the following bands may provide long distance communications during the peak of the sunspot cycle? Okay, so that's going to be the 6 or 10 meter band. I guess it's the peak, the sunspots actually makes it work better. But the sunspots will affect the ionosphere, causes it to work better or worse. So in the 6 and 10 meter bands, it works, it helps them. Why do VHF and UHF radio signals usually travel somewhat farther than the visual line of sight distance between two stations? Well, the radio signals do actually bend a little bit, even VHF and UHF. So it can bend a little bit and it actually goes beyond the visual horizon of the atmosphere. So quite often you can talk to somebody just over the horizon where you can't see, but still get over there with radio. Does radio signals move somewhat faster than the speed of light? It's actually, I think it's a little slower, but anyway. So anyway, those are all the questions associated with antennas and propagation and that type of stuff. So if you can answer all those questions, you got it made. Okay, any questions? Any thoughts? This is a picture of a Yagi antenna. That's a directional antenna. Typically, there's multiple radials like that. That looks like it's probably in the VHF band, the 2-meter band. And as you get higher in frequency, you get up into the 70 centimeter, those radials get shorter. But that's one you can point in a specific direction to get the best signal. Okay, so homework assignment. Sorry we went so late today. Kind of had a lot of stuff to go over. So this coming week, we should be on chapter 4, propagation and antenna feeds. That's kind of what we went over today. So hopefully that'll make sense to you. And please keep taking the practice test. The more practice tests you take, the better you're going to get at it.
So, Dale, what was the chapter we were supposed to have read last week? I forgot to write it down. And,
Oh, last week should have been chapter 5, amateur radio equipment.
okay, I'll go over that again. Thank you.
Okay. Okay, well, we covered a lot of ground tonight. Hopefully that helped a little bit. Any thoughts?
Thanks, sir.
Any questions? Anything that
Thank you.
Well,
okay, well, thank you. I'm gonna go ahead and shut off the recording, and this will be available later tonight.